Log on, tune in, find out. Another good idea from Cambridge.
City and the sum of squares problem.
Okay, like I promised, it's not going to matter much, I hope, if you haven't seen the outlet volume. Yes. Okay? Yeah. It's not going to matter very much if you haven't been here last time, maybe a little bit. So, arithmetic complexity. And the sum of squares. So we'll get to sum of squares at the end. Actually, I have so much to tell you. I think I should have had another lecture on this topic, but anyway, we'll see what we can do today. So arithmetic complexity first, I didn't say last time, but people ask me questions. There are two recent surveys that contain everything I'm talking about and more. There are also books, but more focused on the kind of stuff I'm interested in. There's a beautiful survey that just came out of Spilka and Yudayov, and another survey that will be published very soon that we wrote on partial derivatives and the use of in arithmetic complexity, but actually also for other things like proving Bezout or proving the Veil bound or stuff like that. So should be on the websites. Okay, so we are talking about arithmetic circuits. So these are we are computing polynomials in many variables over some field, which will usually be complex numbers, but can be other in some cases. And we compute them just via multiplication and addition. So we are allowed to have the variables sitting in the bottom, and then we can multiply them, and then we can also add what we multiplied and possibly put coefficients from the field, multiply and so on, eventually computing the polynomial. And we are mainly interested in this S of f, where this is the minimum size of a circuit computing f. And I talked a lot last time about various results regarding the size and also depth. And also about this is so this is a minimal size. This is called an arithmetic circuit. So that's a minimum size circuit for a function, and this is a minimum size formula. Formula is just a tree. And we discussed some, that's a little we know, we discussed a lot of open questions and discussed a few results, few basic results. And really the only general lower bound we have, we don't have much more, is this result combined of Strassen and Bauer and Strassen, that the size of computing x1 to the n plus x2 to the n, xn to the n, is at least some constant times n log n. That's the largest lower bound we have for any polynomial that has degree roughly as large as the number of variables. So we will just talk about polynomials whose degree is about the number of variables, not more. It's not interesting to talk about degrees which are, let's say, exponential in the number of variables. Okay, so that's general, and now I want to start talking about restrictions to the model, and for some restrictions we can do a little better. Although these restrictions will generally be, as you'll see, quite pathetic, and there'll be lots of things we still don't know, even for very, very restricted models. But for these restrictions, I'll put sort of little letters and numbers next to these parameters, and in particular, I'll use this for, I'll use H for homogeneous, and M for multilinear, and for non-commutative. I'll define these models, but basically, I mean, this is what happens when you tell the circuit that you want everything computed in its gates to be, let's say, a homogeneous polynomial. That makes sense if your output is a homogeneous polynomial. Or similarly here, you restrict the circuit to compute at every gate just a multilinear function, multilinear polynomial, and it makes sense if the output is a multilinear polynomial, and so on. Non-commutative we'll get to a little later. So I want to show you, I'll mention some results and I want to prove some, and in particular I want to sort of advertise this partial derivatives. We've seen already the power of partial derivatives, not, well, sort of for a lower bound, this lower bound, but partial derivatives were used, the way partial derivatives were used was via an upper bound on the computation of partial derivatives. Here I want to start using partial derivatives as a way of proving directly lower bounds, so as progress measures. And I want to tell you a couple of results like this, very beautiful results. And before I do that, I want to remind you of some functions that we'll be looking at. So we'll look at the determinant of you know, n by n determinant. So this is of matrix X. The usual determinant, the permanent function. Same thing without the sign. Symmetric polynomial. Some overall subsets of size D of the product. That's an elementary symmetric polynomial. We mentioned others. I don't think today we'll touch upon them, but I also want to use in this lecture the opportunity to advertise the importance of these two polynomials, the determinant and the permanent. They are, of course, familiar to mathematicians, especially this one for lots of good reasons, but that's one particular reason to try to understand them in you know, their complexity. Okay, so the first sort of pathetic model I want to look at is circuits of depth 3. Now, why circuits of depth 3? Because the shallowest circuit that can compute a polynomial is a circuit of depth 2, right? So you can compute a polynomial like this. So this is depth, that's what's called depth 2. But if you are computing a polynomial this way, the size, let's denote it with the 2 here, it will be obvious what I'm saying. So the size of a polynomial in depth 2 is what? What's the minimum size of a polynomial if you compute it in depth 2? You can just know it. What is it for determinant, for example? How many gates do you need if you're computing? Yeah, and factorial. In general, it's always just the number of terms in the polynomial. So that's a trivial model. It's worse than pathetic. So we understand it completely. But we can allow just one level more and try to understand this. So what is depth 3? You can see that you should have the plus on top, otherwise you can compute only polynomials which have factors. So depth 3 looks like this. Here you have products, below them you have sums, and below them you have the variables. Okay, so this is depth 3. What do we know about depth 3? So I said here, for example, S2 of determinant and factorial. What do you know about this? So this is sort of a polynomial. These two levels compute a polynomial, but not in the variables, but rather in linear functions of the variables. Seems pretty, also. Maybe we can understand. Okay. So what do we know? What upper bounds do we have? Nobody knows how to compute determinant better than the obvious ways and in n factorial ways. Somehow the permanent, which in most cases is considered harder than determinant, there is a formula called the riser formula, which does it almost in just 2 to the n, n times 2 to the n. You can think about it. It's just using the inclusion-exclusion principle. It's very, very elegant. Okay, so what about upper bounds? What about, what about lower bounds? What do you think is S3 of the symmetric polynomial? And let's say with some basically, we don't have lower bounds. We don't have super polynomial lower bounds for this model. We just don't know. So let's restrict it even more. Okay. Questions so far? Everything's good. Let's restrict it even more. I'm sure everybody knows what it is. So the restriction I'm going to add is I look at homogeneous circuits. So if I'm computing a homogeneous polynomial like the determinant or the permanent or the symmetric polynomial, then the output is homogeneous. So it makes sense to require or force the circuit to compute homogeneous polynomial in every step of the way. Now it is known that in general circuits it doesn't cost you more than to take a general circuit and make it homogenized or pasteurized, I don't know, is not a real problem. It just costs you some factor that depends on the degree, like this squared. It's a very simple thing. But when you restrict the depth, it doesn't, and by the way, I didn't say it, but when you restrict the depth, you notice that I'm allowing myself unbounded fanning, because otherwise, we couldn't reach the top. So that's a major difference, and now eliminating or forcing a circuit to be homogeneous is not clear how to do. So anyway, we'll look at homogenized lower bounds, and I want to prove to you an exponential lower bound on this. Okay, so here's the first lower bound, so -3. So if you take, I don't know, d to be n over 4, you get 2 to the, you get an exponential lower bound. This is a result of Noam Nissan and myself. So how do you prove a lower bound like this? The important, well, you have to use the homogeneity, and the only way you are going to use it is that in a circuit like this, there's only one place when you see a product gate. And since the output in the case of symmetric polynomial of degree d is of degree d, then this fan-in here, if you're solving this problem, cannot be bigger than d. So all product gates can take only at most d terms. It cannot have more. Or without loss of generality, it doesn't take more, because you can throw away all the product terms that have more than this. So you can assume that all product terms have degree d or less. So now, how is the proof going to look like? as I said, we are going to introduce some progress measure, and we are going to see that the circuit, as it progresses from inputs to output, if cannot generate more and more complex objects too fast. And just the main question in general in circuit complexity, or in a lot of cases in circuit complexity, is just putting your finger on what it is that cannot be, that cannot progress quickly. And in this case, and sometimes these things are really weird. I mean, you take a circuit, it's computing something, and that's what it does. But what you are imposing is, or what you are looking at is other things that are not necessarily computed by the circuit, but are somehow there. And here's what will be there for at least this model, what seems good to use for this model. And this is the following. So if we have a polynomial f, I want to introduce this collection, all partial derivatives of f. Okay, so all partial derivatives, this means that I'm looking, this f is on n variables. So I want to look at this collection, df, dx1, dx2. It will be, the polynomials we are looking at are multilinear, so we never take derivative more than once with any variable. Sorry, xi1, xi2, xij. And this is for all j between 0 and n, and for all I1, I2, ij. So in other words, the collection of all these exponentially many polynomials that are derived from your polynomial. And let me write d of f, or dim of f to be the dimension, the linear dimension of this set of polynomials. Okay? So it's a number, it's an integer. And here's something really neat that I will not prove, but it's, it's an observation, basically, just using the standard things we know about derivatives. And this lemma says the following, that this parameter, the dimension of the span of all these partial derivatives, behaves very nicely with respect to the operations of a circuit, plus and times. So the dimension of a sum of functions is at most a sum of the dimensions. Okay, that's completely obvious, because you just look at all the individual partial derivatives and they span the derivatives of the sum, and that's just because derivatives are linear. And because of the chain rule, you also have the following. So you have any number like this, so any plus gate in this circuit, and you can have coefficients if you want. But also, so because of the chain rule, so as you are computing sums and products of polynomials in this circuit, you are also computing sums and products of these dimensions, and they respect the circuit. Now, if we have a depth-free circuit, so I'm just going to upper bound now, this number for a depth-free circuit of size s and degree of multiplication d. So it looks like this. So we have variables in the bottom. Then we have plus gates. Then we have product gate. This is at most d in each one. And then finally we have also plus gate, which let's say has s things added into it. So S is practically the size of the circuit up to polynomial. So let's look how these numbers progress as we, so let's write here the dimensions. What is the dimension of a variable? Now we'll see that you understand the definitions. So what's it? 2 actually, because I'm including the empty derivative. So it's either the variable or constant. So here we have just 2 for every variable. What's the dimension of a linear function in the variables? It's less. So if you don't take any derivatives, the empty one, then you have the linear form. If you take any derivative, it doesn't matter with respect to which variable, you get a constant. So that's still 2, and this is really lucky. So even at this level we are 2. Now when we take a product of at most d things, we say by this part of the lemma that this is at most 2 to the d. Right? Now when we add s of them by the first part of the lemma, that at most s times 2 to the d. So this is great. We know exactly what is an upper bound on this dimension complexity of a circuit like this, and now all we have to do is give a lower bound for our favorite polynomial, for example, the symmetric polynomial of degree d. I will not do it in any detail, but I'll tell you this other lemma that together finishes the proof is a dimension of and d is n to 0 to 2. I'll just explain where it is coming from.
But you should surely calculate it exactly, couldn't you?
Yeah, but who cares? I mean, it wouldn't give you any different exponential. It's exponential over. If you want, you could, yeah. I think this is tight, actually. Yeah. Okay, no, not, yeah, it's close to being tight. Where is it coming from? This is just linear algebra. Take the symmetric polynomial, the dissymmetric polynomial, and look at its partial derivatives. Just look at its partial derivatives with respect to d over 2 variables, x, I, 1. Take the derivative with respect to some d over 2 variables. Then what do you get? What will be the result? What kind of polynomial will it be? Another symmetric polynomial on fewer variables. This will disappear, and you know, of degree, which is half, right? So what's the span of all of these? You can really easily calculate it just by writing here all these x, you know, x1 up to xg over 2, all monomials. All these monomials, and for each one, you know, once you take these partial derivatives, look at the, you know, coefficient of the remaining polynomials. Also here you put the same x1, same monomials. Just write all monomials of degree d over 2 in the rows and in the columns, and for each one you get a polynomial, a symmetric polynomial of degree d over 2. And what are the 1 and 0 patterns here? So these are basically sets S of size d over 2, and here are sets T, also of size d over 2. And you have 1s and 0s in this matrix. When do you see a 1? You took partial derivatives with respect to this set, so you'll get a symmetric polynomial on all the other variables, so those that are disjoint from this. So this is just, you know, you have 1 here exactly if S intersect T is empty. So this is just the inclusion matrix of the disjointness matrix, and it's not completely trivial, but you can see that this has full rank. This matrix has full rank. So all these polynomials are linearly independent, and because of this you have the lemma. Now you take the lemma and you take this bound, and you get the lower bound written here. Is this clear? Okay, so that's great. So let me go back to this. So it's really powerful, these partial derivatives. We'll soon see another use. Of this, but let me go back to the non-homogeneous circuit model. So it turns out that there is a lower bound here. There is a little lower bound. This is symmetric. If you have degree which is linear, then you get an n squared lower bound. That's a result of Amir Shpilka and myself. And this uses also partial derivatives in a sort of more sophisticated way than what I showed you now. But it uses partial derivatives and some restriction arguments. But anyway, what I want to tell you is something that was known before all these results. Before the lower bound I showed you and before this lower bound that I didn't show you. And this is a result of Michael Ben-Or. So the question is whether homogeneity helps, inhomogeneity helps for the symmetric, computing the symmetric polynomial. And what he showed an n squared upper bound for any d. So if you allow inhomogeneous terms, then you can do it in n squared. You have a formula, it's actually a formula. The formula, I should put here, that these are both for formulas. Okay, let me show you this. To understand what I want to show you, I want to show you this exponential gap between the power of homogeneous and non-homogeneous depth-free circuit.
There's some constant involving d in here, presumably.
The upper bound holds for every d. The lower bound holds for linear d. The lower bound is like n times d or times n minus d, depends if it's bigger or smaller than n over 2. Okay, so I want to show you this result. Let me go back to this board. Can you, any of you, see anything while I'm erasing? Just have to remember your algebra facts. Like last time, this Samuelson identity. Here it's much simpler than this. So let me look at the following polynomial g of t. This is a very nice way to write it, right? The sum. Okay. I guess. Right? So all we have to do is find some particular coefficient of a polynomial, of this polynomial. How do we find the coefficient of a polynomial? By interpolation. If we have n plus 1 values, it's a polynomial of degree n. If we have n plus 1 values of this polynomial, then we have actually just a linear combination of what we have. So that's great. That's Michael Ben-Or's solution. He says, well, okay, let's look at these products. So let's look at them. This one product. So here we have just x1, x2, xn. This corresponds to t equals 0. Here we have a product x1 plus 1, x2 plus 1, xn plus 1. Here we have x1 plus n, n plus n. So you just take n values in your field. Notice the field has to be large enough to contain n plus 1 values. But if it does, then you do this. And here, this is g of 0. This is g of 1. This is g of n. These are n plus 1 values of our polynomial g. So we know that there is some linear combination with some coefficients, alpha 0, alpha 1, alpha n, whose sum will get us. That's it. Okay, so it's amazing. And you notice that it heavily uses the fact that we multiply here much more than d terms. We multiply n terms, and because of inhomogeneity, they cancel. Okay. Questions about this? Okay, so let me tell you just one more basic result that uses partial derivatives and random restrictions in a very important way. It's maybe the strongest result we have right now in arithmetic circuit complexity. It's a result of Ran-Raz, and that's lower bounds on the permanent and determinant. If you restrict, they are multilinear circuits, so if you restrict yourself to multilinear computations. And the lower bound is that if we look at multilinear circuits, now there is no depth restriction. It can be arbitrary circuits. That and the same for permanent. It's a beautiful, beautiful result, and I invite you to look at it at the survey, the first survey, or in this paper. Actually, in the survey, it's simpler. So there are super polynomial lower bounds for multilinear circuits. Okay, now I want to say a few words about why we care so much about the determinant and the permanent. Why understanding them is really all you have to do in order to understand arithmetic circuit complexity. So I'm going to switch gears a little bit and just go back to general complexity theory and remind you a couple of things. I wonder when I'll talk about sum of products. Okay, so we have these classes P and NP, and I'm sure you've all seen them and you like them. And they are classes of Boolean functions. And these are classes of problems that can be computed in polynomial time. And one way to think about it is that problems here are problems where like you are given some circuit, some Boolean circuit, and some input, and you are asked to compute what the value of this circuit on this input. So both of these are inputs, and this should be the output. Any problem in P is sort of reducible to this, because that's the algorithm you have, and that's the input you have to. These are problems in P. Problems in NP is almost the same. You are given a circuit and an input, but the circuit in this case is a circuit that has room for two things. It's a circuit that has some unspecified inputs, and what you should figure out is, does there exist a y such that c of x, y is 1? That's what you should figure out. There's a non-determinism. So that's these are problems in NP. And these are all the Boolean, it's all in the Boolean setting, and we have no way to prove lower bounds in the Boolean setting, and people thought that in the arithmetic setting it would be easier, so they went on and defined classes of problems for arithmetic circuits. In fact, Valiant in the 70s did this, and the classes are called after him, VP and VNP. And what happens here is that here the circuits were Boolean. So now it's allowing arithmetic circuits. Makes sense. So here you are given C and X. This is arithmetic circuit. And you are supposed to compute C of X, just evaluate the input. So these are the kind of things we were building, right? We were building arithmetic circuits for various problems. This is the class analogous to P. These are the things that can be efficiently computed by arithmetic circuits. And what's V and P? It's almost the same, only, so let me specify here the Y. Let's say 0, 1 to the end. So here, you are given C and X, and the circuits are of this form. And what you're supposed to compute is a polynomial. So you're supposed to, instead of this logical operation, you replace it by a sum. So what you ask here, the sum over all y in 0, 1 to the n of C of xy. So you get sort of a count. If the circuit always outputs 0, 1, you get how many are evaluated to 1. For how many y's is the output 1. So it's like a counting version of problem in NP.
Sharp P.
What?
Is that sharp?
This is like sharp P, yeah. It's sort of, these arithmetic circuits, when you make it Boolean again, it is sharp P. Yeah. Now what's the, really remarkable thing that he proved? I just want a notion, just before I say it, I want a notion of reduction. So the notion of reduction we will use. So reduction is a way to translate one problem to another. And for polynomials, there is a very natural way to translate one polynomial to another, and this is by projection. So if we have some polynomial f of x1 up to xn, we have polynomial g of y1 to ym, we'll say that f is easier than g. F reduces to g. This is the analog of polynomial time reduction. Simply, if there exists L, so L is just a matrix. So these are a collection of linear functions. There's a fine version and a linear version. It doesn't really matter. I will just write a linear one. So let's just call the rows here L1, L2, Lm. Just a matrix of coefficients such that f is what you get. F on x1, xn, or let's just call it x. F of x is simply what you get when you plug into y these linear functions of x. So you just translate them by a linear operation, and so you put here L1 of x to Lm of x, and you get back your polynomial. Okay, so it's just that's a projection, a linear projection. So that's a very natural reduction. Certainly, it's efficient, so to speak. So if you have such a reduction and you have a way to compute g, then you really have a way to compute f also. So that's the notion of reduction. Now here's the amazing thing that Valiant proved. He proved that the permanent is complete for this class BNP. So everything that can be efficiently computed in this class can be projected to the permanent. Okay, so let me write it down. If we have any polynomial fn, so fn I mean n variables and degree at most n. If fn is in VNP, then fn reduces to permanent, maybe with, I don't know, n cubed variables. Okay, so if you could compute anything in VNP, then you can project it to the permanent. The permanent is the hardest, and of course he also proved, but that's not difficult. That's an exercise for you. That the permanent can be computed this way. So let me leave it as an exercise. Okay, that explains why the permanent is interesting. It's like the NP-complete problems for arithmetic complexity. Well, we're also interested in the determinant. Questions about the first? Yeah.
Just one small question. If you replaced L1 up to Ln by any easily computable polynomials, would you get a more general notion of
No,
or is it the same?
you won't. No, as long as they are computed by polynomial size arithmetic circuits, then it's the same. And in fact, you can take these linear functions to be projections, real projections, so just a variable or a constant. It's still as general as everything. Yeah. What about the determinant? So the determinant, so this 2 case, right? We have this in VP, right? We have a circuit for. So what kind of completeness do we have? We would like this to be the hardest for P. It's almost like that. So so we like everything that's easy to project to it without any blow-up. Okay. It's not quite. We don't quite know it for circuits, but we know it for formula. So if Fn, if L of Fn, well, let me write it like this. If L of Fn is at most S, then Fn reduces to determinant S plus 1. So anything for which you have a small formula, you can project to a determinant of the same size. This is not difficult. This I recommend as a nice exercise. Okay, so what do we conclude from these two things? What we conclude that in order to know whether the permanent is hard or not, all we have to know is whether it projects to the determinant. Right? So what's the minimum M such that permanent N projects to determinant M? Actually, it's not even clear that such an M exists, but I claim it is clear. By Valiant's result about the completeness of the permanent, it's clear that if you plug M 2 to the N, 2 to the 3M, then it's, you can project, because the permanent is in VNP. And the permanent has formula of exponential size, so it makes sense, this number. And of course, the conjecture, so let's call it M of N. The conjecture, of course, is that M of N is not polynomial. Or you can conjecture what you want, that it's exponential and so on. Okay, that's a basic conjecture. What do we know about this? The permanent can sometimes be projected to determinant. I don't know if you think about the permanent of this matrix. It's exactly the same as the determinant of right? So M of 2 is 2. That's the only case when you have equality. So there were a bunch of lower bounds. First proof is bigger than 7n, and then that it's something like square root 2n. Maybe another result. And then two French algebraic geometers proved the best lower bound that we have. This is Mignon and Rosaire. I want to show you this lower bound. Again, to show you the power of partial derivatives. So it's a quadratic lower bound. With hindsight, it's a trivial lower bound. Trivial not because it's trivial, the proof is not trivial, but just because there are n squared variables in the n by n permanent. So it's really a linear lower bound. But you can see that it took a long time, and you can see that it's not trivial. So then I'll stop. So I'll do it very quickly, then I'll have like 10 minutes to tell you about sum of squares. I'll just write the... How do you use partial derivatives to do this? Well, what you do is you notice that if we have this L that translates, so if the permanent of a matrix X is the determinant of L of X, where L is this, and this determinant. Then, so let me just, HF is the Hessian of a polynomial f or a function f. What is this? It's just you write a matrix, if it's on n variables, it's df, dxi, dxj. So it's the Hessian of a function. Why is it relevant? Well, that's what we sort of use as a progress measure on linear projections. It turns out that if, in general, if you have a reduction like this, so if f of x is g L of x, then the Hessian of f at x is L transpose the Hessian of G at a well-related matrix that comes from this transformation, well, basically L of x times L. So this matrix, the Hessian, is just the Hessian of G, and you just conjugate it on these two sides, and also, you know, this is an n by n, this is an m by m, but these linear transformations. So these are constant matrices. These are constant matrices. Okay, so this applies also here. And all you have to do is just say that, you know, if this is equal, if there is equality here, then the determinant, then the rank. So you just apply this and you get that the rank of the Hessian is the smallest rank of the Hessian of the determinant, the m by n determinant. Okay, just use this. And now you think and you notice that here for every x, and that's a property of the determinant, its variety is sort of flat. It contains, that's what the Hessian captures. Variety contains hyperplanes of very small codimension, about m. So this is always at most something like 2m. And if you are clever, you find here a matrix. So this for every matrix, every y. Well, this is at least n squared over 2. So you have a matrix for which the Hessian of the permanent evaluates to something of high rank. Remember, this matrix is n squared by n squared. It's a matrix, it's all the variables of the permanent. And so you get from this a lower bound. Let me leave you the details. Okay, so let me tell you questions. So I want to tell you a little bit about the sum of squares problem. And so here is the problem. So, Frank, is there a lecture after this one? Are people happy
Sure.
Yeah, there is. Yeah, okay.
Oh, yes, it's
Yeah,
another day.
okay. So I'll just define the problem and tell you the connection and just state the results. So, well, x1 squared that's obvious. Here's another one that you are familiar with. Right? So this is the norm of the product of two complex numbers. What about x1 squared plus x4 squared? y1 squared. Can it be written as a sum of what? z1 squared plus z4 squared. And I'm working over the reals now. zi of xy by linear. So can you or can't you? Some people must have seen this. Yes. You can, because you get here, I mean, you can decipher it from these matrices on the right. So this was discovered by Euler. And independently by Hamilton, like a century later. I'm not sure. This is the formula for the norm of the product of two quaternion elements. And then it didn't take that long. This was done by Cayley and Graves. And you'd guess what this must be, this product of the norm of two octonion elements. Okay, what's the next? What's the next formula? That's it. The buck stops here. So Horvitz proved that the only time where you can write, so in general, let me just ask a question. Suppose we have x squared plus x n squared, y squared plus y n squared is the sum of zi up to k of n. And zi squared versus zi again are bilinear forms. What's the smallest k? So what Horvitz proved is that k of n equals n only if you have 1, 2, 4, and 8. These are the only cases, nothing else. But you can ask, what's the smallest k for which you can do it? This is a sum of squares problem. So what can we say about this k of n? K of n is clearly at least n, and is at most n squared because you can open it up, right? And you can actually improve this a little bit. This is non-trivial. There is a theorem of James that uses algebraic topology to 2 minus Lil law 1 n. So that's a non-trivial lower bound, very non-trivial. And nobody has any idea of a better than this constant lower bound.
That's asymptotically or?
Asymptotic, yeah. So it's 2 minus Lil law 1. That's the best known. Also, the upper bound can be improved. The upper bound turns out to be as most n squared over log n. Not sure how many people will guess where it's coming from, but basically the place it's coming from is Clifford algebras. Okay, so we have these things, and here is we don't know what to do with them. I really want to advocate this problem. This problem, I'll just state two equivalent formulations of this problem, and then I'll tell you why I'm interested in it, what we prove. So, I mean, the problem is obvious enough. It's just stated there, but here are two things that you can do. So suppose you have such an identity from 1 to k to n. So this is equivalent to two things. One is that there is this matrices m1 up to mn. Each of them is n by k matrices, m1 to mn, such that mi transpose is the identity matrix, and mj transpose plus mj mi transpose is 0. This I different than j. So it turns out that sum of squares happens exactly if this happens. And this is equivalent to a problem that's completely geometric or topological, that there is a map, a norm-preserving map from the n spheres to the k spheres, And let me call f by linear. Maybe I should call it z, because there's the function z, which is bilinear and norm-preserving. So z of x, y so on the sphere, I guess they are just 1, so it will be 1. So these are equivalent formulations. And I really would like to, so it doesn't matter what branch of mathematics you come from, you can work on this. And why am I interested in this? I'll just state the theorem which makes the connection. Because we failed so miserably proving interesting lower bounds for circuits, even arithmetic circuits, people start to look at further restrictions on them. In fact, you can think that the arithmetic circuits are restriction of Boolean circuits because they have less relations, right? For example, the relation x squared equal x is not, is there in the Boolean case and it's not there in the arithmetic case. So we remove these relations. It should be easier to prove lower bound. Let's remove more relations. Let's remove commutativity. We know that commutativity helps. Tim mentioned last time that to compute x squared minus y squared, you can do with one multiplication, despite the fact that it seems like you need two multiplications. But that holds only in the commutative case. In the non-commutative case, that doesn't work, and you need two multiplications. So maybe we can prove lower bounds for non-commutative circuits. For non-commutative computation, of course, you have to define an ordering on your monomials. So you can do it for permanent or determinant in the obvious way, by row order and so on. So let me just state a result. So this is the last thing. This in a joint paper with Rubesh and Yehudayov. If k of n is greater than n to the 1 plus epsilon for any epsilon, if you can prove such a lower bound, just a little bit better than linear, then the non-commutative complexity, let's say, of permanent n is exponential. Should mention that we have no super polynomial lower bounds at all on non-commutative circuits. Even on non-commutative circuits, such a restricted model, we have no lower bounds, no super polynomial lower bounds. But if you work on the sum of squares problem and just make a dent there, then you will prove this result. Okay, thanks.
Sorry, I think I just went to sleep at the wrong moment. Where did the non-commutativity come into the last result?
Well, I wish it wasn't there, and there would.
Was it
The assumption is the sum of squares for a general n grows more than linear,
commutative?
right? In commutative, yeah, commutative. The sum of squares is the sum of squares as I presented it. And nevertheless, if you prove this commutative lower bound, which is just superlinear, you have proven an exponential lower bound in the non-commutative arithmetic circuit model, yes.
But then commutative lower bound should be harder, right?
Excuse me?
For the sums of squares problem, isn't the commutative version harder than
The commutative, let's say there's only the commutative version in the sum of squares. Sum of squares is just a normal, I mean, you can define non-commutative version, but I don't know if it makes, anyway, I don't want to define. Sum of squares is a classical problem. I want you to think about the classical problem. This is the classical question about sum of squares problem, okay? And if you can do something there, then you have proven a really interesting circuit lower bound for arithmetic circuits, namely non-commutative circuit lower bound, which is, which unbelievably we cannot do. Yeah.
So what do you prove as a lower bound?
This is that's a theorem we proved, that this implies
Yes,
this.
but for a special case,
Okay, so since you asked, let me mention that you can define kz of n. This k is kr of n. These are bilinear forms in which the coefficients are real numbers. Okay? But you can look, sorry, let me correct something. I wanted to prove a lower bound for coefficients, even complex coefficients. If you can prove this, then we have our theorem. But you can look at the sum of squares. If you look at all upper bounds that are known for sum of squares, they just have 0 plus minus 1 coefficients. They are all in particular integers. So you can, you can prove lower bounds here. You can try to prove lower bounds here. Now, there are lots of works in which people sort of try very hard and they, for example, I told you that it stops at 16. It turns out that it's known that kg of 16 is 32. There are various results. I should use mention Lam and Mu and others who prove results like this. They prove that for certain finite n, the lower bound is such and such. It's never more than twice what n, but anyway, they sort of, and often they understand exactly the number. So what we proved, this in another paper with the same guys, is that this is at least n to the 6. So for integers, we have a superlinear lower bound. We just don't know how to translate it to anything else. But that's a combinatorial problem, and for those who can, I won't state it because my time is up, but this is a combinatorial type of thing. You have to look at these signed Latin squares. You have to understand them, and understanding them gives a lower bound on the integer K of n.
What the answer should be?
It's a great question. I don't think I know. This sort of throws you off. I mean, you would think that it should be quadratic, but this thing throws you off, and you understand that there is, the way you get this is basically from this type of formulations with the matrices. And when you look at these matrices, at this condition, you see that it reminds you of Clifford algebras. To some people who know about Clifford algebras, it reminds them of Clifford algebras. And there are some non-trivial things you can do that. The fact that, if you take this to be somehow you do something, but it has to do with generators of the Clifford algebra. And then, that's how you can prove that once something non-trivial like this exists, you wonder whether there's, others that were not discovered. And, so on. So I don't know what it is, but somehow I'm hoping that it's bigger than n, and that somebody will prove it. We tried pretty hard, but anyway, maybe. I think this problem existed for a long time and people from various different areas were really interested in it. And there's lots of beautiful mathematical work that goes into understanding them. But, so far, just 2n is a low one.